Hello, everyone. I'm Bill Press. I'm currently the treasurer of the NAS, and in that role, I'm a member of the Council Committee on Scientific Programs, which is responsible for organizing the programs of these breakout sessions. The recent advances in the observation and understanding of black holes have been spectacular. And it was obvious to the committee that we should have a breakout session at this time on this subject. Obviously, not every field of science can be represented on this small committee at any one time. And I was asked to organize this session because I worked on black holes a long time ago. And I've noticed that the field has advanced extraordinarily rapidly, especially after I left it. So, of course, I immediately turned to a genuine current expert on this, Ferial Ozel at the University of Arizona, Tucson. And she has organized this session in collaboration with the other speakers. The other speakers will be Katerina Chatsioanu, who is at the Flatiron Institute of the Simons Foundation and soon to be a faculty member at Caltech, and Zoltan Hyman, who is a professor at Columbia University. Let me introduce Ferial to you now to tell you a little bit about her background, and then she in turn will introduce each of the other speakers. She won't need to introduce herself because I'm doing that now. Ferial Ozel is a professor of astronomy and physics at the University of Arizona. Her BA is from Columbia University. She has a master's from the Niels Bohr Institute in Copenhagen, and she did her PhD at Harvard with Academy member Ramesh Narayan. She was also a Hubble Fellow at the Institute for Advanced Study at Princeton. Ferial pioneered the measurement of neutron star radii, which provide constraints on the equation of state for the cold ultradense material of the neutron star. She also carried out the first simulations of the images of low luminosity black holes that guided the development of what she's going to talk about, X-ray observations in the Event Horizon Telescope at millimeter wavelengths. She has been the co-chair of NASA's Next Generation Mission Concept Study for Lynx X-ray Observatory, and she has served as the chair of NASA's Astrophysics Advisory Committee, and she's a fellow of the American Physical Society. Ferial has received a number of awards for her work, including from the American Physical Society, the Maria Geppert Mayer Award, a Guggenheim Fellowship, a Radcliffe Fellowship, a Breakthrough Prize, and the Rossi Prize of the American Astronomical Society. So with that, let me turn the program over to Ferial.
Thank you very much, Bill. And it is my pleasure to be with you today on this black hole session talking about the recent developments. And our first speaker is Katerina Chatsioanu, who is going to be telling us about what we learned about black holes from LIGO. But let me introduce Katerina first. She did her PhD at Montana State University and was a postdoc at CETA in Toronto after that. Currently, she is a Flatiron Fellow at the Flatiron Institute in New York, but she won't be there for much longer. In the fall, she's going to be joining Caltech as faculty. She's a member of the LIGO Scientific Collaboration, and she's the co-chair of the LIGO Matter Working Group. But today she's here to tell us about what we learned about black holes. So I will turn it over to her.
Thank you, Ferial, and I hope everyone can see the slides now. So thanks everyone for being here. Thank you for the invitation to share some exciting results about studying black holes with LIGO. So the theme of this session is, of course, black holes. And the first talk here is going to be about the smallest black holes that we know of. These are the stellar mass black holes. We call them that because their masses are more or less comparable with other stars that we know about in the universe. So they have masses about 20 or 30 times the mass of the sun. So these are still pretty big objects. But later talks in this session, we'll talk about even bigger black holes that have masses millions or billions times the mass of the sun. So discovering black holes and observing black holes is very challenging. The hint is in their name because black holes emit no light. They are black. Every talk in this session will be describing different ways to overcome this limitation in order to be able to observe black holes. The first way to do this is if black holes are surrounded by some kind of matter, if they're around another star or normal material from the universe, maybe that material emits light, emits electromagnetic radiation, and this way we can indirectly observe black holes. Up until recently, 5 years ago, this was the only way we could see black holes. And you see in this diagram, the purple dots are black holes that were discovered electromagnetically from light emitted by surrounding material to them. And their masses are given on the Y, so they have y-axis. They have mass around 5, 10, maybe 20 times the mass of the sun. The second way to discover black holes is what I will be describing here, which is if the black hole is close to another black hole or close to another very big, dense object. In this case, the two black holes will emit gravitational radiation, and as of 2015, we can now directly observe this gravitational radiation from two black holes. For reasons that I will describe in a bit, we actually observe those systems where they're very close to each other. So you can see the blue dots in this diagram are the black holes observed with gravitational waves. And usually you have a pair of two black holes that are very close together and come together to unite and to give one bigger black hole. So these types of signals that we're seeing with gravitational waves currently are what we call transient signals. They start and an end. They have a beginning and an end, and usually last for up to a second, no more than that. So we observe those systems with gravitational waves, and that is a recent development. It happened for the first time directly only in 2015. And because those systems are very extreme, we have objects 30 times the mass of the sun being very close together, traveling at very high velocities. The only way to really understand them is to look at the full equations of general relativity, Einstein's theory of gravity, that describes gravitational interactions, even when the gravitational fields are extremely large, such as when you have two black holes together. So general relativity has some pros and cons. One of its main cons is it's a very complicated theory. It's highly nonlinear. The equations are very complex, and you cannot solve them in their full generality with pen and paper. You have to go to a supercomputer and write some code. Though to be fair to general relativity, as far as theories of gravity are concerned, alternative to general relativity that have been proposed, general relativity is on the simple side. There are a lot more complicated alternatives out there. The pro of working with general relativity and these kinds of systems is that general relativity describes all of gravitational interactions in such a system. Even when you have two black holes very close together, about to merge, traveling at extremely high velocities, general relativity can predict what exactly will happen there. So if you work within the theory, if you can do these numerical simulations, to the best of our understanding, those simulations, to within some numerical accuracy, predict what the systems look like. So with this in mind, here is such a simulation performed by the Simulating Extreme Spacetimes collaboration of two black holes that come together and merge to give gravitational waves. So you see here two black holes, they orbit around each other the same way the Earth orbits around the sun. They're in spiraling, and what you see here, the colors coming out, the ripples coming out, is a depiction of the gravitational waves that these systems emit. So you can think of gravitational waves as an analogy to other types of waves that we know of. If you take electromagnetism, the theory that predicts normal light that we observe with our eyes, if you take the electromagnetic fields and perturb them a little bit, you'll get out electromagnetic waves, normal light that we have been observing ever since we evolved to have eyes. If you perturb the air in a room you're standing, then you'll get sound waves. By analogy to all these, if you perturb a gravitational field, like those two black holes are doing there at the center, you will get gravitational waves that propagate outwards from the system. So these waves leave the system, and eventually they might travel from the system to us on Earth to detect them in our detectors. Unlike Electromagnetic waves, unfortunately, though, gravitational waves are extremely weak. This is why it took us so long to detect them. We've been detecting light literally for millennia, but with gravitational waves, we were only able to do it for the first time in 2015. Just like electromagnetic waves that are caused by charges that are moving around, gravitational waves are, of course, caused by interacting masses. So the two black holes you see here at the center, this motion of the two black holes is what causes the gravitational waves that go out. So if you have big masses that move in certain patterns, this is what emits gravitational waves. And two black holes that orbit around each other are a perfect system to emit strong gravitational waves for us to observe them. Those waves, of course, carry energy, and because they carry energy, energy leaves the system. The system will, of course, have to respond to that, and the two black holes are getting closer and closer together. You will see that as the simulation goes on, the distance between the two black holes slowly decreases. That's because they're losing their energy to the radiation they're emitting. And eventually, because they're losing energy, they will have to get together, merge into one big black hole. So you will see here the simulation will zoom in, slow down a little bit. The black holes here are very close together, traveling very fast. And here they are merging into one black hole. And the final black hole, that is bigger, of course, than the two black holes that came in, rings down, emits any relic radiation it has left. So let's look a little bit the signal in more detail, what the signal looks like from these types of systems and what we observe here on Earth. It's a nice diagram on the left, shows you at the bottom the signal itself, the signal that we observe, and at the top what the black holes look like at the time they're emitting this signal. So early on in this evolution that we are observing here from Earth, you have two distinct black holes that are orbiting around each other. This is the same type of orbit of the Earth around the sun or any of the other planets in the solar system around the sun. Because they are losing energy, of course, the black holes get closer and closer together. This is why we call this an in-spiral, just in spiral, because they're getting closer and closer together. From how exactly this signal looks like, how fast it evolves, how fast it changes, with time, we can measure things such as the masses of the black holes or the spins of the black holes. How strong the signal is tells us how far away the system is. Stronger signals mean that the system was emitted closer to us on Earth. Weaker signals mean on average that the system was further away from us out to huge distances. Eventually, the two black holes will get very close together, and around what we call the merger, they will start touching. Here, the emission is at its strongest. You see that the amplitude of the signal, the gravitational wave signal, it's at its strongest, the frequency is the higher. At this point, the two black holes are basically touching each other. And because they're touching each other, there is no turning back. They will merge into one big black hole that is very perturbed because it was just born, and it keeps ringing out, what we call ringing out, basically emitting any relic radiation it has from the process that gave birth to it. So let's take another look at the simulation, just the late stages, so you can see the merger process in more detail. The black things that you see here are, of course, not the black holes themselves, the singularities of black holes, but they are the horizons of the black holes. This is the region around the black hole that is completely dominated by how the strong gravitational fields created by the black hole, such that nothing can escape from that region. So the two black holes get close together. You see the horizons start wobbling. They touch at this point here. The move itself freezes as well. And another big horizon forms around them and engulfs the two black holes. And in the end, you have one big perturbed black hole. The astonishing thing about events like that is that you have huge amounts of energy colliding with other huge amount of energy. And this process almost looks peaceful. There is no big collision. There is no big explosion. There's no debris flying around. It's just simply a surface, a horizon forms around two black holes and engulfs them together. To observe these systems, of course, there are gravitational wave observatories on Earth. These are what we call ground-based detectors. And I won't go into detail with how they work. That could be the topic of an entirely different session. But right now, the important thing is that we have a global network of such detectors that are extremely sensitive and can sense the distance between test masses that are 4 kilometers apart. We have, of course, the 2 LIGO detectors in Hanford, Washington, and Livingston, Louisiana, that made the first detection of gravitational waves in 2015. But besides that, we now also have detectors in Europe and in Asia that are also joined together in a global network to observe these astonishing events. The properties, of course, of our detector and our measurement tell us exactly what we can see. And the plot here on the left shows you the interplay between the signals that we observe and the detector properties themselves. So the blue, orange, and green decreasing lines are example gravitational wave signals that we have actually observed. And the U-shaped lines, the blue and the red, are the sensitivity of our detector. So the further down this is, the better for us because the more sensitive our detectors are. So that shows you that we can observe things at around 100 hertz, which is the audible band, the same frequency as the sound our ears can hear, which is why we can make sounds of these signals. And I'm also here showing that the masses of the signals, that those 3 signals that were observed, and they have masses about 20, 30, 60 times the mass of the sun. So this is the fundamental reason why we're observing those stellar mass black holes here. More massive black holes that exist in the universe and we would like to observe would emit signals at lower frequencies, where the detector noise you see sharply rises at low frequencies. So anything that has mass above about 400 or 500 times the mass of the sun, unfortunately, we cannot observe with detectors from the ground. The low frequency noise that is caused by seismic motions is really, really detrimental to our sensitivity to these systems. Those systems exist, and we want to detect them, 500 and above solar mass black holes. But in order to do so, we need to leave the limitations of the ground and move to space. With all said, of course, the first detection of gravitational waves, first direct detection happened on September 2015, September 14th, 2015. And you see here an example of the actual data that was observed in the Hanford detector at the top and the Livingston detector at the bottom. And you'll see this pattern that you recognize this pattern seen from the numerical simulations, where early on you have the gray data that look like noise, nothing interesting is happening. And eventually a signal starts emerging, something that looks like a wave, the amplitude increases, the frequency increases, and you have something that looks like a merger. The signal arrived in the Livingston detector in Louisiana slightly earlier than in Hanford. This just has to do with how the detectors are located on Earth and where the signal is coming from. The interesting thing to remember is that for these, as extreme as these events are, general relativity predicts without any simplifications, without any assumptions, what exactly the signal looks like. And thanks to that, even before we had the data, we had a suite of numerical simulations from general relativity that told us what the signals more or less would look like. And when the data came, you see that the agreement with general relativity was astonishing. This is the light blue curve that shows you what general relativity predicted for this signal. Well, the dark blue is a generic analysis that does not assume general relativity. And the agreement between the two is quite astonishing. To the best of our understanding, this event and this merger of 2 black holes was perfectly described by general relativity. When all is said and done, when you have analyzed everything, the conclusion is that this signal was caused by the dramatic merger of 2 black holes with masses about 30 times the mass of the sun, that at the moment they merged, they were traveling at about half the speed of light. This is an astonishing speed for such big objects. And this whole process emitted an insane amount of energy, 3 solar masses worth of energy. This is a staggering amount of energy, especially when it comes from what looks like an otherwise peaceful event. You have 2 black holes peacefully coming together, merging into one, and this event emitted more energy than any other transient event we have ever observed since the Big Bang. But then again, remember, gravitational waves are very weak, So the most energetic events in the universe, we're just now starting to observe them. A lot has happened since 2015, of course. We have seen a lot more signals. These are systems, these types of events happen in the universe all the time. And when our detectors are on, can capture them if the signal is strong enough. And since 2015, we have an extra 11 detections of these systems of 2 black holes merging and another 2 detections of binary neutron stars merging, though I won't be talking about binary neutron stars that much in this talk. We can measure the properties from the signal. That's how we know that their masses are around 20, 30, 40 solar masses. And here's a plot that shows you all those masses, those curves, and capture what the masses of each system that we have observed look like. And you can see that the 2 black holes have masses around this range, 40 times, 30 times the mass of our sun. Going forward, we will, of course, observe a lot more systems. We already have about 11 of them. But as we keep observing and as the detectors keep getting better and better, we expect to see hundreds of these systems in the next few years. And once we have so many systems, we can start answering important questions about black holes. First of all, black holes are like any other astrophysical object out there. They are born in some astrophysical event and they die in some astrophysical event, being the merger of 2 black holes, an example here. And they interact astrophysically with other objects in certain astrophysical scenarios. So by looking at all these black holes, we are hoping to learn more about black holes as astrophysical objects. For example, we can start answering questions such as, are there more massive black holes than this? In principle, we can see 60 and 70 solar mass black holes. Are we going to see those? Where are they? Or more light black holes, less than 10 solar masses. We can, in principle, see them. Are they rare? Do they exist? Are they made in the universe? We can also figure out the relations between black holes. Most systems so far seem to have similar masses. Is that going to hold up? We also seem to have a slight pileup around here. Most of the black holes we see around 30 and 40 solar masses. Is there a deep reason for this? Is there something in how these black holes are made that causes this? Will this hold up with more data? We'll know the answers to all these questions in the coming years as we observe hundreds of black holes in binaries merging. Besides black holes as astrophysical objects, of course, black holes are fascinating because from fundamental physics perspective, they are very weird objects, aren't like any other object in the universe that we know of. So besides that, we also want to test general relativity, and to the best of our understanding with the systems we have today, the black holes that we are seeing are described by Einstein's theory of gravity perfectly well. Besides that, we also want to understand properties of black holes. We want to see more rare events that are not like the bulk of the events that we are seeing. And there are a ton of examples of this, of interesting little things that we can learn about black holes with rare systems. I'm only going to describe one such example here. And you can see this type of system with another numerical simulation. This is again 2 black holes that are orbiting around each other, eventually get very close together and merge. The interesting thing about this type of system is that now the black holes also have spins. Rather than masses, we also have spins, same way the Earth is spinning around its axis. And you can see the spin sort of in the simulation shown. When this happens, black holes have, and the signals they emit have very interesting phenomenology. The system undergoes this, what we call precession. It basically starts wobbling around in space rather than staying fixed on a plane. So when the Earth goes around the sun, it mostly stays on a plane. But if those black holes here have large spins that affect the signal, then they no longer stay on a plane, and the signal correspondingly becomes more and more complicated. Here's an example. In the top, you have a signal, an example signal like most of the signals we have seen today. But if you have this weird effect that could be rare in those systems, in those binary black holes, that's called precession, and the system wobbles around in space, you might have a signal like the bottom, which looks a lot more interesting. You see all these sort of modulations and peculiarities in the signal that we hope to observe as we get more and more signals in the coming years. Okay, so this is mostly what I had to say about black holes. I also want to give you a brief outlook to the future. We expect the detectors, our ground-based detectors, observing collisions of black holes to get better in the coming years and give us more and more systems. And this nice plot here shows you this. So in this plot, us, Earth, is at the very center. And as you go out, you basically imagine going further out in the universe, at larger and larger distances where those binary black holes are. And the different curves, the different arches in the diagram here shows you how far out our detectors can see. On the left, neutron stars, and on the right, black holes. And the blue one, what we call O2, was our second observing run that finished about 2.5 years ago now. And the result of this was that we saw 10 binary black holes and 1 binary neutron star. More and more improved detectors, such as A+, which is currently under construction, will help us see further out in the universe and correspondingly give us access to a myriad of more signals. Additionally, if you go even further out with proposed detectors, such as next generation detectors with a purple, you see that we can look so far out in the universe that we will basically be able to detect all such systems that exist in the universe, all black holes around 30 solar masses merging in the universe, and this is a staggering amount of systems. We will be able to see with third generation detectors as they are currently conceived. And that will give us an insane amount of information, both about black holes as astrophysical objects and black holes as fundamental objects, what their properties are. So this is what I had to say. I'm going to leave you again with this very nice simulation of 2 black holes merging. This has now been placed in front of a star field, so you basically see the gravitational wave distorting how you see the stars in the back. This is what one of those mergers that we have been observing would look like if we were pointing a telescope at it. In reality, we don't point a telescope at it because they're really far away. The next talk will actually legitimately tell you what happens when you point a telescope at a black hole. But for now, this is a nice, simple visualization for us. And I will take any questions. Thank you.
Thank you very much, Katerina, for this nice talk and introduction to black holes with LIGO. We are taking questions from the audience, and I'm going to start with one that we have, and please keep on sending them. Can we use gravitational waves to study what happens at or inside the horizons?
Unfortunately, no, because the horizons are the region where nothing really escapes from. And since light does not escape from them, we don't expect gravitational waves to escape them either. General relativity gives us a prediction for what happens when the horizons join together and the black holes the singularities keep moving towards each other. But it's unfortunately not possible to observe them. The horizon keeps everything from our eyes and ears.
Okay. One more question. The difference going from the Voyager to CE to the next generation detectors is much bigger for neutron stars than it is for black holes. Can you elaborate on that a little bit?
Yeah, so it has to do with a number of things related to how cosmology behaves at these distances. So increasing the sensitivity by a factor of 2, when you're that far out in the universe, it does not always mean that you increase the number of systems you look at by a factor of 8, which is 2 cubed. This has to do basically with how cosmology works. The universe is accelerating, so our normal intuition about Euclidean geometry does not work here. So that is related to that, with the fact that the universe is accelerating and the scalings are not exactly linear when you're that far away from Earth.
Okay. Bill, any questions that you're getting?
No, I think, Farrell, I introduced you at the very beginning, and I believe you're the next speaker now. And Katerina, thank you for a very interesting talk.
Thank you.
All right. Let me share my screen now. Please let me know if you can see full screen. Okay, excellent. So thank you for that very nice introduction. We're going to now delve into directly imaging black holes, in addition to listening to black holes to learn about their properties, as well as about the theory of gravity that is giving us these objects. The Event Horizon Telescope really wants to study black holes, not just directly image them, the light surrounding them, but do this at scales that is close to their event horizon, which is this point of no return. And in order to do that, one has to figure out a couple of things, the first of which is choosing sources. What source should we point our telescopes to that will give us an opportunity to get these very high resolution images on the black hole event horizon scale? So the biggest black holes that we know around us as far as their angular size in the sky are our galactic center black hole and a nearby black hole called M87. It is in the between the arms of the Virgin and Virgo. And M87 isn't the largest galaxy in that cluster, but it is it has a very bright source at the center that we've known about for a long time. And one of its prominent characteristics is this jet, which we've also known about for a very long time, and we've obtained high-resolution images with Hubble, etc. That gives us the indication that there is some activity at the center of the galaxy. This is different than mass scales that Katerina was talking about. We are now talking about billion solar mass black holes, and we are inferring their existence indirectly by looking at the light that is emitted around them, not from the black hole, but from the gas en route to the black hole, and from the dynamics of stars that we can observe around this dark object. So this indicated to us that M87 would be a good target because it is large in the sky. Well, that is not enough. We also need to be able to see down to the horizon without being impeded by the plasma and the light from the plasma surrounding it. This is the gas that the black hole is accreting from nearby stars. And at especially the long wavelengths, such as the 1 centimeter, which is in the radio band, if we did get a close-up image of this black hole, what we would see is something similar to what you're seeing on the slide right now, which is that this gas surrounding it is opaque. So we also have to figure out what the optimal wavelength to study these black holes are. This is something that we've looked at for almost 2 decades now. And what I'm doing here is cranking up the wavelength. And at the point that we reach 1 millimeter of light, what you're seeing is that all that opaque plasma disappeared. We are now at the horizon scales. There is still some gas that's lighting up this innermost region of the black hole environment. And it looks like a crescent because it's rotating around and swirling. And so one side is approaching us, the other side is receding away from us. And what we are seeing is that a hole appears at the center where the light no longer can come out. It's this point of no return. So this is what the black hole, the Event Horizon Telescope set out to do. And here is my paper with my advisor Ramesh Narayan and my collaborator Dimitrios Psaltis from the year 2000, looking for the first time at what this image size would be as a function of wavelength, and we determined that the millimeter wavelength would be the optimal region where we should do this experiment. So we have a target, we have a wavelength. The way I advertise it to you, you would think that this is now going to be a piece of cake. It's large in the sky. M87 is a billion solar mass black hole. Well, it's also far away at the Virgo cluster. So really, when all is said and done, even the largest black hole in the sky is 100 millionth of a degree. So compare that to the half a degree that our moon subtends in the sky. We can't do it with a single telescope. Instead, what we use is a technique called aperture synthesis interferometry, developed for decades by many prominent people, where instead of having one dish to resolve a source in the distance, what you make use of is several dishes separated by as much as the diameter of the Earth, receiving signals at the same time from a distant source, recording it faithfully, time tagging it faithfully, so that after the fact, these signals can be combined into one signal as if it was received by a dish as big as the baseline of between these two telescopes. So this is what's required to directly image black holes, even the largest ones. And this is the technique that we've worked on for many years. And for those of you who are more in the biological medical fields in the audience, I also want to point out that the technique is similar to what you would do in a tomography or an MRI. As you know, the detector turns around the patient, and we're using a very similar technique. Basically, each pair of telescopes at one instant in time gives us one Fourier component of the image, what we call the Fourier component, the spatial Fourier component of the image. And we rely on the rotation of the Earth, which is a little slower than the CAT scan turning around you, the tomography machine. But this is how we fill up the Fourier space more and more by looking with many pairs of telescopes to our distant source and trying to get as much information about the structure of the source as possible. So we've spent more than a decade outfitting telescopes around the Earth that are capable of observing at this optimal 1 millimeter wavelength of light. And this spans anywhere from the Hawaiian telescopes, SMA and JCMT, to the South Pole, to the Atacama Desert in South America, LMT in Mexico. And in 2008, we even included a telescope, GLT, in the North Pole. And SMT, which is Arizona's telescope, is also a central point that has connections to all these other telescopes, increasing our Fourier coverage. So with this array, as this array grew and the theoretical calculations to make use of the data from this array grew, our collaboration also grew. This is from a collaboration meeting in 2018. And obviously this picture doesn't even do justice. It's only a subset of the 200 plus people that have been working on this actively. In April of 2017, we took the first, what we call the full array observations at the time, the telescopes that I showed you on the map. And you can see that most of these pictures show blue sky or sun, which is great news because that means little water vapor in the atmosphere. We had a great time doing the observations. And actually here, this is the control room, the makeshift control room we set up in Cambridge, MA, getting information from all of these sites and making decisions about when to observe. So that happened in April of 2017. Then it took until November of 2017 to actually gather the data into correlation centers, one in Cambridge and one in Bonn in Germany. The reason being we physically have to ship these disks. It's 5 petabytes of data. It's the actual physical weight of these exceeded 0.5 ton. And of course, the flights from the southern hemisphere, from the South Pole, had to resume before we were able to get all of these disks in one place. Then we went through a step called correlation, which is what I was explaining to you, where you match up the wavelengths of light that are time tagged at different places. Then you fit a waveform to it that is called fringe fitting. And we do imaging. Each one of these steps, as you can see, reduces the data volume anywhere from a factor of 1,000 to 10,000. And that took until August of 2018. And in 2019, April, a year ago exactly, we were able to make the announcement of having obtained the first image of a black hole and accompanied by 6 papers in the Astrophysical Journal explaining the variety of technical aspects of this discovery. So I'm sure you've seen this, the exciting donut, but really, why were we so excited about this donut? I mean, surely the hole in the center means something. It looks half glazed. One side is brighter than the other, sort of like the ones that I showed you before. So what I would like to do in the rest of the talk is to tell you first that we really are sure that there is a hole in the center of this donut, and that is the very exciting part as far as understanding properties of black holes and understanding the theory of general relativity in a new regime. And the second thing I would like to do is to tell you, okay, now that we have this image, what did we learn about black holes? What did we learn about the specific black hole at the center of M87 and about the theory of gravity overall? So, a crash course in Fourier transforms. The data on the right is everything that we have obtained from these telescope pairs as they rotated, as the Earth rotated and took a good look at M87. It's color-coded. And the primary characteristic of this data, when we look at amplitude as a function of the separation between the telescopes, is that it has this ringing pattern. Starts high, has a minimum, then goes up again, and probably has another minimum. This ringing structure in a Fourier transform is very telling. It tells you that there is a compact source with sharp edges. So how do we understand what that compact source looks like? I'm putting the same data now on the right-hand side of the slide, the Fourier amplitude as a function of the separation between the telescopes, and the data are all in red right now. And just for a trial, let's put a disk with no hole in the middle of the size that we roughly expect for what we know about the black hole at the center of M87. The size that we expect for the donut scales linearly with the mass. So given that it's a few billion solar masses, this is our trial. As you can see, the green line does not do a good, even though it has this ringing, it doesn't do a good job of fitting the red data points. Well, what can we do? We can change the size. Okay, we're getting there. We can now model the first part, but as you can see, the location of the first minimum did a good job of getting the image diameter, but the rest of the ringing is not good. In order to get that right, the salient feature, the prominent feature of this image is that it is actually a ring and not a disk. Not only is it a ring, but it is a fairly thin ring. So there is a sizable hole in the middle. And finally, because we don't have infinite resolution, I'm also going to blur it to the size of the telescope resolution. And there you see it. Without doing anything terribly fancy, the visibility data, the Fourier data, is screaming at us that there is a ring there. Obviously, this is a toy model just to demonstrate to you what we've done. We've done lots of different shapes, but the key message here is that, yes, we are certain it is a ring with a hole in it, and we can measure its size very precisely. We've also done many imaging techniques where we assume less about what the source looks like. So we divide up the image space into pixels, and we try to just get the data right by coloring the pixels with different amount of signal. Obviously, there are far more pixels than there are data, so we also use what are called regularizers so that nearby pixels don't change independent of one another. And just like I showed you what that ring does compared to our data, let me also show you what this imaging algorithm does with the data. So let's say that the first trial is what we have on the left here with some blobs that are bright in the image space, and the green on the right, that's darkish green on the right, is going to be what that looks like. So as we do more and more iterations, what you will see, this is now in two directions. It's not asking for azimuthal symmetry like in the previous example that I showed you. But what you see is that, again, with these sophisticated imaging domain algorithms where we allow pixel-based models with some regularizers, we again get this donut shape. So the image elements that are exciting and that we would like to not just use to understand the black hole properties, but also to understand whether general relativity is a complete description of gravity, are the shadow at the middle, or this flux depression, brightness depression at the middle, which we call the black hole shadow, the surrounding plasma causing this narrow ring of emission, and this north-south asymmetry. The southern part of the image looks brighter than the north side. So how do we understand these and how do we make use of them? For that, let's turn to what general relativity told us black holes would look like. And there are some characteristic radii in the space-time of black holes, in this fabric surrounding the black holes, that are extremely important in determining what their visible or observable characteristics look like. And this was first worked out for the Kerr metric by Bardeen Press and Tucholsky Press, being none other than Bill Press, our esteemed session chair. And what this tells us is that there are a few radii at various distances from the black hole as a function of the black hole spin that are going to play a key role in what happens to matter. The first is the ISCO innermost stable circular orbit, inside of which matter does not have stable orbits that it can circle the black hole with, circular orbits. We come a little bit closer to the black hole. There is a very interesting point, which is called the photon orbit, which is the point where light itself, when it has a tangential velocity with respect to the black hole spin axis, can actually complete full circles. So it can still escape to infinity. It can also go into the black hole. But the most important thing is it can stay there for quite some time. Interior of that is the event horizon, which we deem the point of no return. So let's look at this photon orbit a little bit. Even though we're after this point of no return, it turns out that the photon orbit is going to play a huge role in determining the image characteristics. This is from a simulation that you can play with online from Leo Stein for different black hole spins that are marked with the little a, the black hole spin parameter. What you're seeing is that this photon orbit is not a circle, but it's actually a sphere. It precesses, but it still fills a sphere that is a very well marked distance from the black hole. So what that means is that there is going to be this demarcation radius outside of which light that is generated by the plasma around the black hole, the swirling hot gas around the black hole, is going to come out. There is one radius in which it's going to spend time perhaps circling around the black hole, making it brighter, and the interior of that is going to be quite dim, giving rise to the black hole shadow. This was actually calculated for the Kerr metric by Bardeen and Luminet in the 70s, but for a very idealized case, somebody kindly holding a torch on the other side of the black hole, giving rise to this ring. But let me also show you what that looks like in a little simulation. So if we shine light from one side of the black hole, or even all around the black hole, it turns out to not matter. What happens is that all the rays that are marked in blue end up falling into the black hole, and all the rays that are marked in red are able to get to an observer at infinity. So the size of the shadow is a very well-defined characteristic given the mass of the black hole. Not only is the size very well determined in the Kerr metric, but what we what we can say is that their shape is also very well determined. They are actually highly circular. One might expect that changing the spin of the black hole has an effect on this, but this was shown about 10 years ago, that when we change the spin of the black hole through a very interesting cancellation in the frame dragging and the quadrupole, we actually have the circle moving to the right as we increase the spin of the black hole. But of course, the center of that image has no meaning. And until we get to very extreme spins, it is actually highly circular. Not only that, but where the observer, we are, with respect to the black hole also doesn't matter. We can be looking at it completely face on, down the spin axis, or edge on, perpendicular to the spin axis. And the only difference it is going to make, either in the shape or in the size of the black hole, is limited to just 4%. So what does this give us? This says that if we are able to identify the shadow and measure its size, we can measure the mass of the black hole. It also tells us that if we know the mass of the black hole through other independent means, this is going to give us a good comparison, a null hypothesis test of the general relativity theory, and we are able to recover any deviations from Kerr if they exist. So going from those highly idealized space-time only cases to realistic cases of low luminosity black holes like that in M87, like that in the center of our galaxy Sagittarius A star, is actually quite complex, because it involves really understanding how matter falls in, how it heats up, what role do the magnetic fields play in that environment. And when somebody is not holding a flashlight, but the source is close to the black hole but scattered, how does that translate into images? So as a community and as the Event Horizon Telescope collaboration, we spent nearly 2 decades making these simulations better and better, involving new technologies in order to speed up our calculations, like GPU platforms and certainly high performance computing. This is a very involved calculation. And what I want to show you is that we indeed generate with our theoretical models of the gas and the thermodynamics and of the radiation, images that look very much like what we observed in M87. And as an example, I'm showing you from 2012, just in case you think these are done after the fact. In fact, as a collaboration, we've done such a large parameter study that we were able to really identify all the different ways in which the complications of the surrounding gas could manifest itself. Could it obscure the shadow? Could it make thick rings instead of thin rings? And how does this depend on the black hole spin, etc.? So using these, we were able to learn quite a bit about the black hole in M87 using this technique that I was just mentioning to you. We measure the image diameter, either directly from the image or by fitting models like I showed you, those ringing, beautiful rings with some asymmetry in the Fourier domain itself. We use these large suite of simulations, these theoretical simulations that I showed you in the previous slide, in order to calibrate when the shadow size is affected by the properties of the plasma. And then we also use this theoretical uncertainty in where the observer is and in the black hole spin in order to get from the size that we measure of the black hole shadow into the mass. And we've done this. This is just a compilation of all the different techniques that were used to measure both the width of the shadow of the ring and the diameter of the shadow. And you can see the clouds of points coming from different techniques. And using all of this, these are the image domain, these are the Fourier domain models. What you will notice is that the image domain models have larger fractional widths. That is by construction, because the effective beam of the telescope is 10 microarc seconds. So it's not possible to measure something in the image domain that is smaller than that. Whereas direct modeling in the Fourier domain with those rings and crescents showed us that the image itself could actually be a thinner ring. So with that, we were able to find that the mass of the black hole is 6.5 billion solar masses, and the image diameter in the units that we're interested in was 42 microarc seconds. So this is, as I said, not only seeing that point of no return, this demarcation by the photon ring and the effect of the horizon interior to it, but also getting some astrophysics out of it. So as a final point, what I want to say is that the shadow size and shape is also going to allow us to test general relativity. And the way we do this is we say, what if the space-time of the black hole is not Kerr? Can we get sizes and shapes that are much different than what Kerr predicts? Because it's so well defined in the Kerr metric. And Katerina pointed this out earlier. She said alternatives to GR are even more complicated. That is very true. So we work in these alternatives to GR to understand what the shadow size and shape would look like. And indeed, you can get pretty much anything you like, certainly non-circular shapes and shapes that are much larger or smaller than those in the Kerr metric. So using this, we compared the mass that we obtained for the black hole with the one that we had earlier prior to the EHD from the dynamics of stars around M87, shown in this dashed blue line. This is the EHD measurement in purple, the stellar dynamics measurements shown in blue, and there is excellent agreement to date between these two. There is just for completeness, let me also mention that there is a gas dynamics measurement that predicted a different mass for M87, and the difference with that is the one in red. So right now, what we can say is that there is no reason for us to suspect that the exterior space-time of M87's black hole is described by anything other than the Kerr metric. But this is going to go on. We're working on the data for our galactic center black hole. We're also working on the shape, not just the size. So stay tuned for more updates from the Event Horizon Telescope. Thank you.
Thank you, Fayral. That's terrific. We actually received a couple of questions by email, if I can bring them up here. Bob Wilson asks, has useful data been collected yet by EHT of the black hole in our galaxy? And if not, what technical obstacles make that observation more difficult?
That is a very good question. We certainly collected data on Sagittarius A star at the same time that we collected data on M87. And let me go here to show that one more time. So in the 2017 campaign, we had wonderful data from Sagittarius A star. In 2018, we got some more, although the weather wasn't as good. The problem with Sagittarius A star is that it is a smaller mass black hole. We know it very precisely. Unlike M87, there is just no doubt about what it is. It's 4 million solar masses with even more precision than the numbers that I'm quoting. And because the mass is smaller, the time it takes for the gas to circle around it is faster. What we call the dynamical time scale is shorter. Because of that, let's go to the 1 millimeter again. And what I'm showing you here actually is a simulation for Sagittarius A star, where what you see is during the time it takes for us to do our tomography with this Earth rotating and getting a good look at the patient is moving around. We say, don't breathe, don't move your arms and legs, but this is what it's doing. So it is taking a little bit longer for us and different techniques for us to reconstruct images from this less cooperative black hole. But certainly we are on track. There are some nice results in there, but we have to iron out the details.
Okay, and then a final question, maybe just very quickly. Maybe I missed it, but is there a way to put a number, an upper limit on deviations from GR for some, generic kind of deviation? Is this a 30% test, a 10% test, a 1% test?
Very good. So what we get from the mass is about a 15% test. Let me show it here again. So the 68% confidence in this, when we compare to the stellar dynamics mass, is about 0 plus or minus 15% deviation from the Kerr metric. But I didn't have time to talk about it in this context. We also have a very nice first measurement coming from the spin itself, the shape itself, not spin. And there we're putting a maximum deviation of 10%. So we're asking ourselves, how non-circular could the shadow be and still be consistent with the image that we have obtained? And the answer there is maximum of 10% deviation based on shape.
Okay, very, very interesting. Thanks for a great talk. I've learned that in addition to Academy members and their guests who are watching as part of the national or annual meeting, rather, we have about 400 members of the public watching this talk.
Wonderful.
I hope they're all still there. Now, Farrell, putting on a different hat, let me turn it back to you to introduce the third speaker, Zoltan Hyman.
Okay, thank you. So going from the stellar mass black holes to the ones that I talked about at the center of galaxies, our next speaker is going to tell us, well, how did they get to be there? How did the black holes grow from the early universe onward in the centers of galaxies? And to do that, we have Zoltan Hyman, who was born in Budapest and grew up there. He moved to MIT for his undergraduate and received his PhD from Harvard in 1998. He was a postdoc at Fermilab and then a Hubble Fellow at Princeton prior to joining the faculty at Columbia University in 2003. Zoltan is very involved in black holes. He's been a core member of the LISA science group and the lead for multi-messenger astronomy for LISA, as well as a member of the science and technology definition team for the LINX telescope, this concept study that we mentioned before, being the co-lead for the first black hole studies with LINX. For his work, he's been recognized with the Blavatnik Award for Young Scientists given by the New York Academy of Sciences in 2010 and the Simons Fellowship in Theoretical Physics from the Simons Foundation in 2016. He's going to tell us what he can in about 25 minutes, but he is a co-author of the annual reviews entitled The Assembly of the First Massive Black Holes, coming out later this year. So if you're thirsty for more after his talk, please consult that annual reviews article. Zoltan, take it over.
So thank you. Thanks, Farrell, for this nice introduction, and thanks, Bill, for inviting me to this session. And I hope we can interact in person at some point. My talk will focus on the obvious question that is raised by the previous two talks. As you just heard, we are now absolutely sure that black holes exist in the universe, and we want to know where they actually came from. So that is the topic I will address here. I want to do three things in this talk. Quickly overview once again the observational situation of these two types of black holes. Then the bulk of the talk will be theoretical, trying to explain where they come from. And then I just have a couple of things to say in the future, how we might actually settle this question forever. So as you just heard from the previous two very nice talks, we have two kinds of black holes in the universe. One is stellar mass black holes, and these are masses, their masses range from between, let's say, 10 and 100 solar masses. And their remnants, they're actually very well understood. There's not much more I need to say about this in this talk. They're the end results of stellar evolution. If stars are massive enough, when they exhaust their nuclear fuel, they will collapse to a black hole, and gravity cannot, the collapse cannot be avoided. And we actually know two ways directly that these black holes exist. One is from the first talk we just heard from Katerina. When they're paired up with another black hole, they emit gravitational waves, which have been detected. And curiously, another way to see them directly is when they have another kind of partner, just a normal star, from which they can steal a material. And this material then falls onto the black hole and makes it very bright as it dissipates its energy. These are called X-ray binaries. And so there are a few dozen of these in our galaxy and in the nearby universe that we know about, but we actually know that there are maybe tens of millions in our galaxy that we have not seen of such stellar mass black holes. It's just that we can only see them when they're in binaries. Now, the supermassive black holes that I will really focus on in these talks are actually quite different. There's only one or perhaps a couple in each galaxy, and they sit in the nucleus. And there's actually ways to see these, again, in the nearby universe. One was the talk we just heard, very nice direct imaging by the Event Horizon Telescope. This has only been done so far for one nearby galaxy, but may be done for our own galaxy as well in the nucleus. Another technique by which these black holes are seen is simply when the angular resolution is high enough, we can see either stars, as shown in this picture, in our galactic center, or gas that's moving so fast in such a compact region that these velocities approach 10% of the speed of light. So we can infer with very high degree of confidence that there is a massive black hole there. The masses range from 10 to the 6 to several billion solar masses. Now there's one important point, which is all these observations probe only the nearby universe, or the present state of affairs. But supermassive black holes in the nuclei of galaxies are actually, can be some of the brightest things on the sky when they act like so-called quasars. So just like for an X-ray binary, where the black hole steals the material from a nearby star, the material that falls into the nucleus of a galaxy can accrete onto a black hole, this million to billion solar mass black hole, and make something that's called a quasar. These quasars are really bright, and that's very important because we know that we are able to see them at extremely high distances, which probe the very, very early universe. So there's actually a million, roughly, of these quasars that have been cataloged. And as you go to farther and farther distances, there's a record holder, which is currently a quasar whose mass is almost 1 billion solar masses. It was discovered a couple of years ago. And it's so far away that when this quasar existed and emitted the light that we now detect, the universe was only about 690 million years old, which is 5% of its current age. And so we know that somehow nature manages to manufacture very large black holes very early on in the evolution of the universe. And therefore, the question we need to understand is, where do these massive black holes come from, and how come they're present so early on? Now, if I poll the audience, I'm sure people are very creative, and you can immediately come up with at least 3 ways. You could ask me, well, Zoltan, we can make black holes the following ways. Well, we just heard there are stellar mass black holes. Well, first of all, we just heard, that's number 3 on this list, is that there are stellar mass black holes, which we know are in the galaxies, and we know that they can merge together. So you can maybe hope that so many mergers happen that they make a very large black hole. We also just heard that black holes are surrounded by plasma, which they can eat and grow, presumably during this process. So like Ferial showed, there's plasma around the supermassive black hole, and it's being eaten by the black hole. So maybe it can grow by accretion. I'm going backwards on this enumerated list. A third option that you might come up with is, well, why don't you just have a large cloud of gas which is able to collapse, and instead of forming a star, it just makes a big black hole. It turns out that these ideas are, let's say, poking around the correct notions, but they just don't work as stated. So this idea of collapsing a gas directly into a massive black hole has the problem that if you take such a cloud, it's not spherically symmetric. It tends to collapse inhomogeneously, and as it cools, it fragments into little pieces and forms normal stars instead of a giant black hole at the center of mass. We could also say that a single stellar mass black hole might grow, but unfortunately, this accretion rate is basically very low because these black holes are found in regions where the gas densities around them are very low. For example, the parent star, which left the black hole behind, ejected the mass from around the neighborhood by its radiation. Plus, the accreting black holes, when they accrete efficiently, they tend to be very bright, and that tends to push on the stuff falling into them and forbid the material from actually reaching the black hole. And as far as the mergers are concerned, we do know this happened. We just heard from Katerina, but there's just way too few of these mergers in a galaxy, even in the dense nucleus, to build up at the early times a giant, massive black hole. Now, because these ideas don't work so simply, we need to think a little harder and ask, well, how did the universe become so clever that it made these massive black holes? And the solution, first of all, I should say off the bat that we don't actually know the answer, but we have very good ideas we've developed over the last, let's say, 10, 20 years. And probably the answer lurks in the fact that the conditions in the early universe were very different from the present day universe. So first of all, the early universe, when it was, let's say, 10, 20 times smaller than today, was much denser. And the galaxies which formed then were forming in very huge numbers, and they were very small, as I'll explain in a second. And most importantly, the gas in the early universe, which filled up all of space and the forming galaxies, was very chemically primitive. Now, these first galaxies appear, and maybe starting at about 100 million years after the Big Bang, and the process which leads to their collapse is essentially the fact that gravitational pull of a slightly overdense region in the early universe causes this region to separate from the expanding universe. First, it just expands more slowly, but then eventually it stops expanding entirely and recollapses on itself. And in fact, there's a mass limit, a lower limit on the mass of such a cloud that can separate from the expansion, because the gravity must overcome the pressure. The gas has pressure, which tends to resist the collapse. And as you know, when you compress something, here the compression is done by the gravity, which pulls the cloud towards its center of mass. But if you just think of a bicycle pump, when you compress gas, in this case the air in the pump, as you compress the pump, the gas pressure rises and it halts, makes it very difficult to push further. So just this process does work. The gravity overpowers pressure, but then creates this pressurized cloud of 1 million solar masses. It's denser, of course, than the rest of the universe, but we need to form a star, so we need to continue collapsing. And that means the pressure somehow needs to be deflated. And normally this happens in our galaxy. So a cloud, a star-forming cloud, which ends up producing a star at the center in its collapse, is doing this by radiating its energy by excitations of molecules. So as shown here on the right, if you have molecules in the gas which collide during the contraction of this cloud, then the molecules can get excited into their excited rotational vibrational states. And then these states decay back to the ground state and emit photons, which tend to be in the infrared. And the clouds don't interact with these photons much. These photons leave, and effectively you're converting the collision speed of molecules to photons, to radiation, which leave the cloud. So you continuously cool the cloud and allow it to continue collapsing. Now this is controlled by molecules which made of mostly actually carbon and oxygen. And this is why the early universe differs quite significantly. So this is the periodic table, of course, today, and there are many interesting elements which can form molecules and atoms which can cool radiatively plasma. But the early universe looked very different. As probably a majority of the audience knows, in the Big Bang, we did not produce all these elements of the periodic table. We only produced, Big Bang only produced hydrogen and helium. And this actually makes the situation very dramatically different. The only way this proto-galaxy can radiate its energy is essentially using hydrogen, either hydrogen molecules, which are not as complicated as this molecule here shown on the right. It's just 2 protons and 2 electrons, but it does have vibrations, rotations. And the key point is that unlike in our galaxy where the gas cools to 5 Kelvin, the energy levels of the much more simple hydrogen molecules are much higher. And so once you cool down to 100 Kelvin, there's no way to cool further and lower the temperature further. If you, for some reason, do not have molecular hydrogen and you just have hydrogen atoms in the collapsing cloud, the hydrogen atom, first, the lowest lying level is actually even higher. So you can cool to a temperature of 10,000 degrees, but below that, it's impossible. So these clouds would be very hot. Now, we can say with confidence that this formation of hydrogen molecules, in fact, controls the fate of these first stars and black holes because it controls the temperature of this plasma. And therefore, I'll show that in a second. I just want to know that first discuss the expected abundance of molecular hydrogen in these clouds. So molecular hydrogen form in this way. It's a 2-step process. It's not using anything other than hydrogen and electrons. But the molecules can also be destroyed if there's radiation impinging on this cloud from nearby objects which had already formed in the universe by essentially a photodestruction, by exciting the hydrogen molecule, by absorbing these radiation into its excited electronic states. So these are 12 EV photons which hit the cloud. And this is quite a complicated calculation, but we actually know the impact of this radiation on the molecular abundance. Most recently calculated by my student Gemma Walcott-Green. Now, you can use this information and run an actual simulation, 3-dimensional hydrodynamical simulation, starting from not quite the Big Bang, but not much far beyond, where you have essentially no free parameters. You follow the collapse of a cloud. We know all the initial conditions, and we know the molecular chemistry, so you can follow these clouds, which are millions to hundreds of millions of solar masses, starting to appear a few hundred million years after the Big Bang. And we can see how material, in fact, is compressed by gravity into the center. This is the density distribution. This is the temperature. And the key point probably of this entire talk is that this inflow rate into these clouds somewhat paradoxically increases with temperature. And that's because if the gas remains hot, because it's so chemically primitive, then the speed of sound in this gas is high, and gas doesn't like to move faster than the speed of sound. And therefore, in a hotter cloud, it's somewhat counterintuitive. It's hotter, so it will have to be slightly larger and will collapse later. But when it does collapse, it collapses at much higher rates, proportional to the cube of the speed of sound. And so as a result of this, there's the 3 possible outcomes of what actually happens in the core of such a collapsing cloud. So for reference, as you go from left to right, the left one is corresponding to a cloud in our galaxy, in the nearby universe. It's this cloud in the middle is collapsing and cooling efficiently down to 5 Kelvin. The accretion rate, the inflow rate in the center region is very small. And you basically end up with a normal star. This is, we understand, the formation of massive stars. Now, if you have a cloud in the early universe which did not suffer sufficient impinging 12 eV radiation, it will form some molecular hydrogen. It will still be much warmer, and the temperature will be 100, 200 degrees Kelvin. The accretion into the center will be 100 times faster, and you tend to end up with stars which are about 10 to 100 times more massive than would form in a normal nearby universe. And the important point from this is that instead of the star population we have in our galaxy, where only 0.1% of stars are massive enough to produce a black hole, in this case, we have most of these early stars will end up producing a black hole when they die, and they die very rapidly after about 1 million years. And then the third and most interesting for us is the scenario where you had enough impinging radiation on this cloud that the molecular hydrogen was destroyed. So it only cools by exciting atomic hydrogen. Temperature is now 10,000 degrees. It collapses much more rapidly at solar mass a year rates. And then what happens is you produce a star which keeps growing. And the process is actually very interesting. I won't go into details, but what you form is a supermassive star. It can keep growing essentially without limit. It keeps accreting solar mass a year for about 1 million years, after which point general relativity predicts that the core of this object is unstable and starts collapsing and forms first a small black hole, but very quickly eats the rest of this supermassive star. And you end up with 1 million solar mass black hole. This is very interesting, and it essentially says that the first method, which I talked about, where the gas collapses directly into a massive black hole, it's not quite like that. It first goes through this stage of a supermassive star, but essentially the end result is the same. So we solved this problem by the nature of the chemically primitive nature of these early clouds. Now, in fact, the very high accretion rates are also relevant for solving the second way of this forming a supermassive black hole, which is if you start with a stellar mass black hole, which I just said are very abundant in the early universe, if one of these finds itself in such a cloud, because the cloud already formed one star, and then the rest of the material falls in so rapidly, this, it turns out, also results in a very massive black hole, which very quickly grows to about 1 million solar masses. And so here's the couple of slide explanation of this. So the problem, which I mentioned earlier, is that if you have a cloud collapsing, but then you start accreting in the middle, and you have this essentially a very small quasar, it starts shining light, which tries to push on the material that's falling in. So this radiation impinges on the infalling clouds, and the inward gravity is cancelled by the outward radiation pressure. This phenomena should be familiar to people, and it essentially means if you try to feed a black hole faster and faster, it's brighter and brighter, and eventually it's so bright that it pushes the infalling gas away. So this means there's a universal maximum feeding rate. That's called, for historical reasons, the Eddington rate. And it just means if you try to feed the black hole at above this rate, it doesn't really go in. This was a state of the knowledge until a couple of years ago, that therefore it's impossible to quickly grow a stellar mass black hole to a supermassive regime. However, we managed to circumvent or understand that this limitation doesn't apply in our regime, where the solar mass a year inflow rates are so high that they're thousands or even 100,000 times above this critical Eddington rate. And so it's essentially that overpowers this radiation. And the two steps to that, which I want to explain, is here is now another cartoon picture. This is the black hole. This represents a slab of material falling towards the black hole. And there's some radiation generated here, which the key point is that this radiation doesn't come out in straight lines from this cloud. It bounces around, because this gas, if the feeding rate is so high, this gas gets extremely dense and the photons scatter. So they try to execute a random walk coming outside of this cloud. And in fact, you can show that there is a region here, although not an actual horizon. It is, for practical purposes, a horizon, because the photons in this region, the outward diffusion speed is slower than the infall velocity of this material, so they just swept in with the plasma. So they never come out. So effectively, the black hole is not radiating. It's swallowing its own radiation in this region. Whatever can come out is still actually dangerous, could shut down the accretion. But we've also shown that this radiation is much smaller, because the large fraction of the radiation generated here is already swallowed by the black hole. And this residual radiation, when it impinges on the material that's captured by the black hole further out, it's not able to fall in at this when the inflow rate is so this radiation is not able to stop the inflow. I mean, the main result of this calculation is that the inflow rate has to be order 1,000 times larger than this critical Eddington rate, but in fact we do realize that in these early galaxy simulations. So I think I'm basically concluding here that there's a very interesting ways to produce black holes in the early universe. And the last one slide, I want to just mention that there are ways to test these theories with future observations. And one is by LISA, which was mentioned before. This is a space-based version of LIGO, which can detect mergers between massive black holes, essentially at these very early epochs, essentially to arbitrarily large distances as far as we care about, and can map out the early population of growing black holes whenever they merge, which is very different in these different scenarios. And then links the X-ray telescope and the James Webb Space Telescope, the successor to Hubble, has a chance to directly detect the light produced during the accretion and collapse of these black holes. So there will be tests of these. We have to be slightly patient. We're trying to probe very, very distant and very faint objects, but it should be possible. So here are my conclusions. If you want one takeaway point, which is sort of counterintuitive, the largest black holes in the universe, whether they form and when and how, it's probably controlled by the little hydrogen molecules forming out of primordial plasma. There are ways for this relatively warm gas in the early protogalaxies to result in supermassive black holes, either by hyperaccretion or supermassive star stage. And I hope we can test these models within the next decade or so. Thank you.
Thank you, Zoltan, for this very enlightening talk. I do hope that we will get these next generation telescopes to learn even more about these early universe black holes. So we are open to questions from the audience. Please email them if you have any in the next couple of minutes. We have one question that is asking, could there be massive black holes outside galactic nuclei?
So yes, that's a very good question. When I started the talk, I mentioned that these supermassive black holes, there's only one or a couple in the galactic nucleus. And in fact, the answer to the question is that yes, these large black holes can be ejected from galaxies. They must form in the galactic nuclei because that's where the material is very dense and can result in these processes I described. However, just like we heard from Katerina, when two black holes merge, they emit gravitational waves. So if two galaxies merge and they have these black holes in their nuclei, then the analog of the LIGO detections can take place, which is the two supermassive black holes approaching one another and then eventually merging and emitting gravitational waves. What I think was not yet stated at this session is that the emission of these gravitational waves is not isotropic. They carry not just energy away from the binary, but also momentum, linear momentum. And to conserve momentum, the remnant black hole recoils. This is a very interesting phenomenon. And the recoil velocities are independent of mass, and they are in hundreds or thousands of kilometers per second. So if such mergers take place in galaxies, the nucleus containing the merger remnant black hole may not be able to hold on to this merger remnant, which may fly out of the galaxy. How frequently this happens is something we've been modeling, but it's actually quite feasible that half of the supermassive black holes have been ejected. And we just have no ways of seeing them because the space is so tenuous. The plasma density is so tenuous in between galaxies.
Okay, thank you. I think we are just a few seconds from the end of our session. Bill, should we wrap up or do one more question? What do you think?
I think we can probably elegantly time out at exactly our stated time. So maybe I'll take this opportunity to thank the three speakers, Zoltan, Ferial, and Katerina, to thank the audience for listening to this session, and to thank the National Academy, of course, for hosting this and giving us the opportunity to get the public even more interested in black holes than I know they always are. So thank you, and I guess we're done here for today.
Thank you.
Thank you.
Thank you.